Hi everyone. This lecture is an extension of the previous lecture, which was also about Bitcoin networks. So we'll be extending on the ideas discussed in the previous lecture, and we'll also be going into a little more detail on some of the topics discussed earlier. So just to give you a preview of what we discussed earlier, so we talked about the topology of the Bitcoin network, which is to say that things are flat and everyone is equal in that network. We also discussed things such as how a new node which wants to join the network would proceed to do so. So the address discovery mechanism was discussed, where it pings a seed node and then it learns slowly over time what the peers are in the network and starts to connect with them. We also discussed things like the flooding algorithm, which is how information such as transactions that come up are propagated through the network. We'll be going into a bit more detail in this specific area, so we'll talk a lot more about information propagation specifically in the lower level, what messages exactly are sent and received. We'll also be discussing things like what happens when information propagation is slow. So what happens in delays caused by information propagation, those sorts of things, and how they connect to things like blockchain forks. We also discussed full nodes and SPV nodes and functionalities of nodes. So those sorts of things happened in the last lecture. We'll be building on those concepts and moving forward. Before we get into the core idea, which is basically that we'll be discussing here, which is basically an in-depth look into the information propagation and aspect of the network, we'll be having a small discussion on another implementation detail that we left out in the last lecture. So this would be the idea of pools in the Bitcoin network. So the way that these things work is, sure, we have a huge blockchain which is building over time, and this blockchain is being stored in the persistent storage of these nodes that participate, which can be in the vicinity of hundreds of gigabytes. So, for example, we know that it's over 300 gigabytes now. So, however, there's also some memory pools that are used, which are basically stored in the local memory of each participating node, and each of these pools have some functions. So, the transaction pool, which nodes store, it's basically used to keep a list of. It's basically a temporary list where all of the transactions that have come into this node, but those transactions are not yet a part of the blockchain, i.e., we expect them to eventually be incorporated, but they're not yet. So all of those transactions, they're kept in a temporary local memory. So we can call that the transaction pool. Another very interesting pool that we have, basically a temporary storage that we have in the Bitcoin network, is the concept of orphan pools. So what are orphans? What are orphan transactions? Basically, as the name implies, orphan pools store orphaned transactions. So an orphan transaction is one where, remember how we view transactions in the Bitcoin context, right? So a transaction is merely a set of inputs that lead us to a set of outputs, and those inputs must be consumed in the form of those outputs. So if we as a node are to receive a transaction where we cannot say for sure what the input is, for example, it refers to an input, but we haven't seen the input transaction yet, but we've received the transaction that uses the output of that input transaction and uses that in this current transaction. So it refers to an input which we don't know yet. So for all of those transactions where the input refers to a transaction that we haven't seen yet, we'll say that these are orphaned because if you remember from previous discussions, if you use a previous transaction as an input, you call that the parent of this current transaction. So because the parent is missing, we say that these transactions are orphan transactions. Note that the reason for storing this is we will probably see the parent at some point later on, because the reason that transactions sort of come out of order is because the network is huge, and because of the large size of the network, it might be the case that child transactions, which refer to parent transactions, which are supposed to have been created later, it is possible that these transactions arrive earlier. So what happens is, in all of these cases, we store these child transactions in an orphan pool. Now, what happens when we find a parent that was previously missing? So when that message comes in late, for example, and we make that connection that this is in fact the parent of this child, we will immediately remove the child from the orphan pool because it's no longer an orphan, and that becomes a proper transaction now. Furthermore, any other transaction which may have been a descendant of this parent transaction which we found just now will also be removed from the orphan pool because we now have a complete chain of the complete chain of history. So as a result, all of these orphans are now set to be validated and they will all be removed from the pool. So yeah, so as we discussed earlier, these are stored only in local memory, and these are populated and emptied dynamically as transactions come in. As we find that these transactions are eventually either incorporated into the blockchain, that's when we take them off the memory pool, the transaction pool, and when we find the parent transactions of these orphans, we take them off the orphan pool. So as a result, these are stored only temporarily and not actually kept in persistent storage. Now we'll be discussing a more in-depth detail, in more in-depth detail, the process of information propagation in the Bitcoin network. So we'll get into the exact messages that are exchanged to pass information from one node to another. Note that when we say information, we really mean transactions and blocks. Those are the important information that need to be propagated. So when a node has either mined or received a new block, it wants to alert its neighbors to the presence of the block. So what it will do is it will send out an inventory message. Now, the inventory message is usually unsolicited, meaning the neighbors don't really ask for this message. What the inventory message does is when a node that receives a new block, when it sends out the inventory message, it gives a detail of the inventory of objects that this node has. From this inventory, the other node can realize, the other neighboring nodes can realize that maybe this node has a block that they don't already have. If this is the case, if the other nodes do not have this block already, they'll request that block from the node that has sent out the inventory message. As a result, what happens is they'll send out a get data message, and once the original node that sent out the inventory message gets the get data message, it realizes that its neighbor wants the block, so it will send out the block, which is visualized in this diagram as you can see. So this set of three message exchanges eventually allow for the transfer of a new block from one node to another. So in the context of information propagation, we now know that there are three messages that are important. However, not all messages are equally sized. Of course, if you think about it, the inventory message is basically just telling you that, hey, I have a block. And the get data message is saying, I want a block. But none of these messages are like particularly heavy. There are small bits of information that alert the other nodes or the node that's transmitting it about either the existence of a block or a neighbor wanting that block. However, the message that actually transmits the block, the last message that you see here, is actually pretty large because the block limit of Bitcoins is 1 megabyte, and lately blocks have been touching that limit. So meaning that's a 1 megabyte. That's 1 megabyte of information that needs to be transmitted across. So if you give it a bit of thought, you'll realize that the block message, that the size of the block can contribute to delays, and that's precisely what we'll be going into now. So now we'll be discussing what these delays are like and what impact that these delays have. So as we've been discussing, there will be a propagation delay from at each hop. So by hop, I mean when information goes from one node to a neighbor. And the bulk of the delay, as you might have guessed by now, comes from verifying the block. So the block has a whole lot of transactions inside it. All of these transactions need to be verified. That is, we need to make sure that these transactions are valid. Also, we need to make sure that the coins that they're spending are unspent coins. All of those things take a lot of time. At the same time, you also need to transmit the actual message across the network. That also takes time. So both of these things contribute to a propagation delay. Now, to particularly investigate how that propagation delay looks like, we will be discussing an experiment from a pioneering paper by Decker and others from 2011. It's referred in the slide. So what this experiment does is it's going to try to see how long the delay is on average. Basically, when can we expect most of the nodes to have seen the message or have seen the blocks? As a result, we'll try to see the distribution of that delay. So basically, the rate at which most nodes get it, and how long it might take us for all the nodes to have listened to the message. So what we're going to do is, according to that experiment, we're going to set up a measuring node. So all that the measuring node does is it sits there in the network and it listens for inventory messages from other nodes. If a node sends out an inventory message, it means it has received the block. So this is a very convenient way for us to know that a node has received a specific block. So we can track inventory messages for a specific block, and we can try to note down when that message is received. So basically, that's a very high level overview of the experiment. Obviously, there's a lot of more details. You can refer to the paper for those details. So basically, the summary here is that the propagation delay, it forms what you might call a double exponential pattern. So first, as you can see in this diagram here, a huge number of nodes. So this is basically a probability density function based on the number of nodes that are receiving the block. So first, you see a huge spike in the number of nodes that have received the block. This is because initially most of the nodes have not heard of this block. So what they'll do is they'll basically all they'll basically all get the data from the neighbor that they hear about it, and immediately they will all send out their inventory messages. However, as nodes start to as nodes have already received those blocks, eventually those inventory messages will fade out, and eventually there will be a shrinking number of nodes which have not received this message. So this is also exponential, but in the other direction. So it'll slowly, there will be a long tail here that goes on, and slowly, eventually, all of the blocks that we look at will have received this message. As you can see, the scale here goes all the way up to 60 seconds. So there's quite a bit of delay between when a block is originally announced and when most of the network has already listened to that block. So the other important thing that must be fairly intuitive from here is propagation delay is positively related to the block size. So the larger the block, intuitively, it will take longer to verify all the transactions that we talked about. At the same time, it will also take longer to just physically transmit. As a result, so if you have a bigger block, it is likely that the propagation delay will take longer, will be larger. So these propagation delays, this is what specifically leads to the blockchain fork. This is why, because there are delays across the network from one hop to another. This is why some blocks come in before others and some blocks come in afterwards, even though that might mess with the actual orientation of the blocks. This is because of these delays that we get at each step. So this leads to blockchain forks. We've already discussed about this, so we won't spend too much time on this here. The important details here are as follows. Firstly, in the case of a blockchain fork, suppose you have a blockchain of your own and you receive a new block from another blockchain. Now, if you remember the concept of a block height basically means how high you are on the blockchain. So it's an indicator of the length of the blockchain as well. So if you receive a new block with the same block height, you know that this block is a parallel chain, right, of equal length. Now, if this block conflicts with your existing block, what you will immediately do is you'll just dismiss it, because these are all the same length, so it doesn't the other blockchain necessarily doesn't have higher priority. So you go with what you know best. You go with the block you got earlier. However, parallel chains can happen where blockchains don't have equal length. What do you do then? So, for example, if you look at the figure here, so this was a blockchain that diverged into two parallel chains because of the propagation delays that we discussed earlier. And here, the chain that continues on in the color of orange, this chain has gotten much longer than this chain. So say you have a node that is on this forked chain. So you have a node that has the following chain. These three blue blocks followed by this green block. What happens when you receive this last orange block that goes back, that last orange block when you already have a blockchain that looks like this, these four blocks? So you're on this alternate chain and you receive this orange block from the much longer alternate chain. How do you merge this? Because the longer chain, of course, has priority. So how do you go about adopting the longer chain as your own chain? So what you're going to do is you've already committed this green block, and maybe in the future, in other cases, there might be even more blocks that you've committed, but still this chain is shorter than this chain. So say you had two green blocks here instead of one as well. In these cases, what you do is you would roll back all of the new blocks until the point where the two chains meet at a common ancestor. So in this case, in this diagram, you see just the one green block. So you would roll back this green block and you'd see this blue block. And this blue block is the common ancestor between these two different blockchains. So you would roll back, or you would roll back all the transactions up until these blocks, which are this block, this first common ancestor block that you meet, and then you would adopt all of the blocks from the longer chain as the blockchain, because the longest blockchain is assumed to be the correct blockchain. Now, if you think about it, the fact that blockchains can fork into several chains because of these propagation delays really opens up the whole system to attack. How so? So imagine that you want to revert a transaction in the blockchain. What kind of transaction might you as an attacker want to revert? So for example, suppose you bought a product from a merchant who has already shipped the product, and you've also paid for the product through Bitcoins, for example, in the blockchain. And you want to make this transaction go away, because if this transaction goes away, those coins still belong to you, and you would have basically conned the merchant, because he thought originally when he saw that transaction that you did pay him, and you did actually pay him because that block was committed into the blockchain. However, if you were a really powerful attacker, there is a way in which you could revert that transaction. What would you do? You would make up a new transaction which conflicts with the original transaction at a height which is less than the height of the transaction that you want to revert. So say that the transaction you want to revert is at a height h. What you would do is you would create a new transaction that conflicts with that original transaction. Say you would create another so say the original transaction says you paid the merchant. You would create a new transaction, for example, that says you paid yourself. And you would make this at a height which is less than the block height of the in which the original transaction was. Then what you do is, assuming you had a lot of CPU power, i.e. over half of the power in the network, you would build on this alternate chain, and you would keep mining blocks, and you do it really fast because you have so much computational power, and you would outpace the honest chain, which originally was the chain, and you would keep adding blocks at such a rate that you would overcome the honest chain, and then your chain, where you basically made another transaction, you put it earlier in the chain, and this transaction conflicts directly with the original transaction. So in your case, you have made an alternate chain where you basically paid yourself instead of paying the merchant, and that chain you were able to grow it so fast that it became the de facto blockchain. As a result of this, the original transaction would be rolled back at all the other nodes, because you would then be broadcasting your really long chain to the network, and someone would be defrauded on the other end. So that's definitely a huge scope for attack that exists because of this, because of the fact that blockchains can fork. One of the things that is used as is important as a defense against this, because note that the idea is you need to have more than the important idea is, we won't get into the theoretical proof behind it, but as we discussed earlier, you need to have a really strong hold of CPU power. Basically, you need to be at least in control of half the CPU power of the entire Bitcoin network. So one way we can try to defend against this is we can keep increasing the difficulty of proof of work. So the reason that we do so is CPU power is getting more and more available, and CPU power is becoming cheaper anyway over time. So if you kept the difficulty constant, and we've already discussed this, so if you kept the difficulty constant, the time to discover a block would get really short. So to keep the time to discover a block constant, what we do is we keep increasing the difficulty. Now, because we've already been increasing the difficulty for so long, and the Bitcoin network has been around for a decade now, or more. So because we've been increasing the difficulty for so long, it's unlikely that one individual would have the amount of CPU power needed to have half of the entire CPU capacity of the Bitcoin network, and no such single entity actually exists. So this is a good enough defense against this sort of attack. However, forks are a problem, and we would like to have ways to improve this issue. So going back to the paper that we mentioned earlier, where we had an experiment where we saw how the nodes, how the delays actually work with each of the nodes. There were a few suggested solutions to this issue, and we'll be going over them because those are interesting for us here. So a few things we can do to reduce the delays, because the delays cause the blockchain forks, because the delays lead to a misordering of the blocks, or they lead to some blocks coming before some blocks coming afterwards, those sorts of issues. So what we can do is we know that the delays come from verifying the block, right? And the verification delay basically comes from two parts of the block. The first part is checking the initial difficulty. So for example, basically we just make sure that the nonce is valid on the block. So the proof of work has actually been completed by the miner, and that this block can actually be trusted. That we need to make sure. The other verification that takes a lot of time is validating all the transactions, because we need to make sure all the coins are unspent and all that stuff. What we can do is we can send the inventory message this was a proposed improvement right after we do the nonce check. So right after we make sure that the blockchain block is valid, we can immediately send the validation the inventory message, announcing the block to everyone else. As a result, what we would do is we would send out the inventory message, and other people can ask for it, and we can propagate the block faster. However, if we later realize that the transaction isn't actually valid, we can just stop. Similarly, we can give the inventory message immediately. So we can think of this as pipelining, basically. So we will, as soon as we receive a block, before even doing anything, we can send out the inventory message. As a result of this, what will happen is basically whenever we give out the inventory message, the other nodes will be like, give us the block, right? Because if it's a block that they haven't heard of, they would want to have access to it. So we'd get a lot of get data messages, but it might be that we haven't actually even finished verifying any of the block. So, or we haven't even gotten the actual block, because we are immediately forwarding the incoming inventory messages. So for example, say the message comes to block node A, who immediately forwards the inventory message to node B, who immediately forwards the inventory message to node C. So now C will obviously forward it to its neighbors as well. However, the actual block might not even have come to C yet, because A gave it immediately to B, gave the inventory message immediately to B, and B gave the inventory message immediately to C. But it's not guaranteed that the actual block has already come to C. So what we do is we will wait to respond to the get data messages until we actually receive the block, because we're immediately forwarding it. It might be that we haven't seen the actual block yet. So these modifications were implemented in an alternate implementation of the BitCoin network. And upon doing so, the researchers responsible for these suggestions, they were able to show that this reduces forking in the network by over 53%. So of course, the BitCoin network that we've been discussing has some limitations. One limitation that we can immediately take off is the forks, right? So Bitcoin's the blockchain network can fork, and that's an issue. Other issues are there are a lot of hard-coded limits in Bitcoin and also in the other coins that come up. So there are a lot of hard-coded limits that really limit the efficiency of the network, you could say. So for example, the block size limit is fixed, as a result of which, and also we force the block mining time as well, so that they are separated out by 10 minutes. So because of all of these reasons, things like the performance of the network, so how many transactions can you really process per second, those things can be limited. At the same time, note that the network uses some fixed hashing algorithms. And these hashing algorithms work for now because we don't know how to break into them. We don't know how to go the other way and figure out the input from the output. However, this can be the case in the future, as a result of which this network would basically fall apart. So we would, at that point in time, we would need new ways to hash. So these are sort of restrictions or limitations that already exist in the network, and there are obviously scopes for improvement going forward. But especially the first issue, which are the limits in blockchain, these are not very easy to implement because because the network is already working within a set of rules and regulations, and changing these sorts of hard-coded limits often means upsetting important balances. As a result of which, some of these limitations will likely go on.